0-day brief.
I was reading through our sources for today's deep dive, and honestly, it completely changed how I look at the device I'm using right now.
Oh, yeah?
Yeah. I mean, have you ever wondered how your computer can open the exact same program 10 times instantly without crashing your memory?
Right, you click, it opens, you click again, it opens again with, zero hesitation.
Exactly. It feels like magic. But today, we're going to show you why that exact performance magic is, well, an attacker's best friend. Welcome to the deep dive. We are looking at a fascinating and frankly urgent security briefing from May 2026 titled The Page Cache Linux Most Dangerous Abstraction.
It is a remarkable document. What we are analyzing here is a deep structural breakdown of how Linux handles memory.
Right.
And more specifically, how its relentless quest for ultimate speed, what developers call zero-copy optimizations, has created this recurring security nightmare.
Yeah, and we are talking about fundamental, decades-old design choices here, right? Things that are actively allowing attackers to gain total system control today.
We absolutely are.
So I want to read the exact cold open from this briefing directly to you, the listener, because it sets the stakes perfectly. It starts like this. If you follow Linux kernel security, you've seen the pattern. Every few years, someone finds a way to turn a zero-copy optimization into root. Dirty COW dirty pipe. And now, in May 2026, Dirty Frag.
3 different bugs, 3 different entry points over the span of a decade, but they all share one common victim, which is the kernel's page cache.
And the briefing makes a crucial argument here, right? This isn't just a case of bad, sloppy coding by some individual programmer.
No, not at all. It is a massive structural vulnerability built into the very architecture of modern computing.
Wow. Okay, so to understand how these catastrophic bugs keep happening, we first need to understand the mechanism Linux uses to save memory in the first place.
Right.
Which brings us to the page cache itself.
So think about the physical limitations of your hardware. Memory, or RAM, is incredibly fast, but it is finite.
Very finite.
Yeah. If every single time you launched an application, your operating system had to physically load a brand new isolated copy of that entire program from your slow hard drive into your fast memory well, your computer would crawl to a halt.
You'd run out of RAM almost instantly, I imagine.
Exactly. So the page cache is this performance miracle designed to solve this.
Yeah.
It ensures that every file exists only once in memory.
Okay, so hearing you describe this, it sounds less like making a photocopy for every user and more like a public library.
Oh, that's a great way to put it.
Like imagine a city library where every single book exists only once. When you want to read a chapter, you don't go to a copy machine and get a personal stack of paper. You just walk to the shelf, open the physical book, and read the actual pages.
Right.
So if 3 people want to read that same book at the exact same time, they're all literally looking at the exact same physical piece of paper.
That is a perfect way to visualize it. When you run a common program on a Linux server, say the superuser command, Ultraubuntu Linux doesn't waste time or space copying that entire program into your specific process's memory space.
It just gives you directions to it.
Yeah, it just hands your process a pointer. It's essentially a map to the exact same memory pages that every other process on the system is already using for that file. It is a shared whiteboard.
Which is brilliant for speed. I mean, 0 copies, instant launch, and you only ever have 1 copy of every file taking up space in memory, no matter how many hundreds of processes are touching it.
Absolutely.
But sharing a whiteboard creates an obvious problem. What happens when I want to draw on it?
You've hit on the core issue right there. Sharing creates trust, and trust creates an attack surface.
Right.
To make the shared library work safely, there has to be a golden rule. And in Linux, that rule is called copy on write, often abbreviated as COW.
COW, okay.
Yeah, so you can share the library book all day long if you are just reading it.
But the second you want to pull out a pen and write in the margins, you have to make your own private copy first.
Yes. You share until you modify, then you fork.
Yeah.
The kernel steps in, makes a private duplicate of that specific 4 kilobyte chunk of memory just for you, and lets you modify that new copy.
So the original library book stays clean.
Exactly. Now, the common misconception is that the kernel is this all-knowing boss that has a master list of exactly who holds what shared pages at all times.
It doesn't.
The briefing points out that this is totally false.
And this introduces the concept of the sticky notes, right?
Yeah. So in the Linux kernel, you have massive sprawling subsystems, the network department, the file system department, the cryptography department.
Okay.
They are constantly passing these memory pages around to get work done quickly, But instead of a central database, they use internal flags.
Right.
Think of it as slapping a Post-it note on the cover of the library book before handing it to the next department, saying, hey, this book belongs to the central library. Do not write in it.
Wait, that makes zero sense to me.
How so?
The file system, the network, and the crypto departments are all in the same building, handling the exact same physical memory, but there's no central librarian.
Nope.
There's no database tracking who has what book at any given time. They seriously just rely on sticky notes passing between completely isolated departments.
They absolutely do.
But why build a system so fragile?
The answer is pure performance. If you have a central librarian, you have a central bottleneck.
Oh, I see.
Every single time a piece of data changes hands inside your computer, which, by the way, happens millions of times a second, the system would have to stop, get in line, and check in with the central desk.
That would ruin the speed.
Right. Decades ago, the architects of Linux intentionally chose blinding speed over centralized safety. They accepted the risk of the sticky note system.
Wow. Okay, so since Linux relies on this incredibly fragile trust system instead of a central librarian, we really have to look at what actually happens when that trust breaks down.
Yeah, it's not pretty.
The briefing walks us through the historical precedents here, starting with a bug that probably lived on the Android phone in your pocket for nearly a decade. Dirty CIW, which was discovered in 2016.
Dirty CIW was a monumental vulnerability. Like you said, it was hidden in the kernel for about 9 years. And the briefing accurately describes the mechanics of this as a photocopier race.
A photocopier race. Okay, so remember the golden rule for you listening. If you want to write in a shared book, the kernel forces you to go to the photocopier and make a private copy first.
Right.
The attacker in Dirty CIW found a tiny flaw in how that rule was enforced, like a timing window measured in microseconds.
Exactly. The mechanism relies on overwhelming the system to create confusion.
How so?
Well, the attacker uses 2 parallel threads. Thread A tells the kernel, I don't need this shared page anymore, drop it. The kernel begins to process that request.
Okay.
But a split second later, thread B accesses it again, signaling it wants to write to the page.
Oh, see.
Yeah. So the kernel pauses and says, oh, you want to write to this shared page? Let me initiate the copy on write process and make you a private copy.
So while the kernel is metaphorically standing at the photocopier, in the middle of making that private copy, the attacker sneaks around the back.
Precisely.
They use an internal memory backdoor called procselfmem to force a write to the original shared page before the copying process actually finishes.
They slip their own paper under the copier lid at the very last microsecond.
Wow.
And the write lands directly on the shared page in the page cache. The library's only copy of the book is now permanently modified with the attacker's code.
So anyone else on the system who requests that file gets the corrupted version.
Exactly. It's fully compromised.
That is wild. And then 6 years later in 2022, we get Dirty Pipe. And the briefing calls this one the sticky note that wouldn't come off.
Yes, dirty pipe. So this bug involves pipes, which are really just memory buffers used to pass data from one program to another. And Linux has this brilliant shortcut called splice. It's a zero-copy trick. Instead of wasting CPU cycles copying data from a pipe to a file, splice just hands the memory pages over directly.
Sounds efficient.
It is. But the problem arose because the pipe had a sticky note on its pages that flagged them as writable.
Oh, I see where this is going. So the attacker opens a pipe, fills it with data, and ensures that writable sticky note is firmly attached.
Yep.
Then they use that splice shortcut to hand the pipe's pages over to a completely read-only file in the page cache.
The critical failure is the handoff. When the page was transferred, the writable sticky note survived.
It just stayed on there.
Yeah, it did not get cleared by the receiving department. So the next time the attacker writes into their pipe, the kernel looks at the page, sees the sticky note that says writable, and blindly follows the instruction.
Oh my gosh.
It writes the attacker's data straight into the cache pages of the read-only file, completely ignoring file permissions.
You know, the distinction that stands out to me here is so fascinating. Like, for you listening, Dirty CIW was a race against time, right? An exploitation of physics and microsecond delays.
Right.
But Dirty Pipe was just taking someone else's sticky note entirely too literally. It wasn't a complex math error. It was just a giant communication breakdown between departments.
That's exactly it.
Yeah.
The pipe department said, these are writable. The file system department never double-checked, and the kernel just did what it was told.
Which brings us directly to the brand new threat detailed in our briefing, the May 2026 crisis. Dirty Frag.
Yeah, Dirty Frag.
If Dirty Pipe was a sticky note that wouldn't come off, Dirty Frag is the catastrophic result of a sticky note that was never written in the first place.
This vulnerability is really a masterpiece of chaining small, seemingly harmless behaviors into a complete system compromise.
It's terrifying.
It starts with the same splice, shortcut from Dirty Pipe, but with a different target.
Let's walk through the heist setup. The attacker wants to modify that superuser file, usr-bin-su. They splice the file into a pipe, so now the file's memory pages are sitting in the pipe. Next, they splice that pipe into a UDP network socket.
And here we have to compare this to TCP. When you perform this exact sequence with TCP, the networking code path diligently slaps a label on those pages that explicitly says, shared, do not modify.
Right.
The TCP team added that safety label way back in 2007.
Okay, so if the TCP team solved this in 2007, how did the UDP team handle it?
They didn't.
What?
Yeah, the UDP code path was written a full decade later in 2017, and the engineer who wrote it completely forgot to add the label.
You're kidding.
No, the sticky note just wasn't there.
So you have these highly sensitive memory pages sitting in a network buffer, completely unlabeled. Anyone looking at them assumes they are standard private network data.
Exactly.
Now comes the actual heist.
Right, so the attacker triggers IPsec. IPsec is the kernel's built-in VPN encryption system. IPsec, in the name of performance, has its own zero-copy fast lane. It wants to decrypt incoming network data directly inside the packet's memory buffer to save time.
Makes sense.
But it is only supposed to do that if it firmly believes the buffer is private.
And IPsec looks at these UDP pages. It sees no sticky note.
Nope.
So it assumes, great, these are my private pages, nobody else is using them. And it uses its fast lane to decrypt ciphertext directly into the memory buffer.
Yes. 4 bytes at a time, 64 consecutive writes, silently overwriting the cached files pages with the attacker's malicious shellcode.
Wow.
And this is where the attacker displays an incredibly deep understanding of how the kernel handles errors. Because they just dumped raw shellcode into an encryption buffer, the resulting decrypted data is going to be garbage from IPsec's perspective.
Right.
The cryptographic HMAC integrity check is going to fail.
Wait, let me pause you there. HMAC, for anyone not elbow deep in cryptography, that's essentially the digital wax seal on a message to prove it hasn't been tampered with, right?
Basically, yeah.
Why would an attacker intentionally fail the security check? Doesn't that ruin the exploit?
You would think so. But the attacker feeds the system corrupted data, fully expecting the wax seal to be broken. They want the HMAC check to fail.
Why?
Because they know exactly what the kernel does next. When the integrity check fails, the kernel says, this network packet is invalid, drop it.
Okay.
But, and this is the fatal flaw, the kernel does not bother to undo the write it already made to the page cache during the decryption process.
Oh, wow.
Yeah?
Damage to the library book is already done.
Exactly.
The system throws away the envelope, but the shellcode is already sitting in the core memory of the operating system, just waiting for an innocent user to run that file. That is chilling.
It really is. It is a chain of 3 completely independent facts. UDP misses the label. IPsec has a fast lane. The HMAC failure doesn't invalidate the page cache.
And none of these are inherently fatal vulnerabilities on their own.
Right. But chained together,
Yeah.
it is a full privilege escalation.
And it gets worse because the briefing notes that researchers didn't just find this one bug, they found a whole family of variants.
They did.
There's one called copyfail that uses the crypto socket API instead of IPsec. And they specifically highlight one called RxRPC. What makes that one so dangerous?
So the RxRPC variant is brutal because it uses an entirely different network protocol that completely bypasses the security defenses container hosts usually rely on.
Bypasses them completely?
Yeah. Normally, cloud providers use user namespaces to isolate hostile code. RxRPC doesn't need those permissions. It works even on hardened, isolated cloud containers.
All of this chaos because of one missing line of code. For 9 years, it sat there in the UDP path, waiting to be found.
9 years.
Which brings the Linux community to an incredibly bitter existential divide. We're looking at Section 4 of the briefing now, process versus architecture.
Yeah. The blueprint for disaster here is relentlessly consistent. You share pages, you add a sticky note, and then you just hope that millions of lines of code written by thousands of different people over decades will always respect that note.
But surely we just need better management of this. I mean, if I'm a developer writing a brand new zero-copy feature today, couldn't we just enforce stricter code reviews?
You'd hope so.
Like, use better linters or automated checklists to make sure I know about a sticky note rule invented by a networking team 10 years ago.
So you are voicing what the community calls the process view. This camp believes the problem is a human documentation failure, solvable with training and checklists.
Makes sense on paper.
Sure. But the other camp, the architecture view, fundamentally disagrees.
How do they counter that?
By pointing to the sheer, terrifying scale of the machine.
Right.
The Linux kernel is over 30 million lines of C code. It is constantly evolving, with asynchronous contributions from all over the globe. Human beings physically cannot hold that much context in their heads.
30 million lines. Yeah, that's impossible.
And when a memory handoff happens dynamically at runtime, you cannot run a static automated script to verify if the receiving end understands what it is holding. The state is just too fluid.
So the process side says fix the human, and the architecture side says the machine is fundamentally broken.
Exactly. The invariants of this entire memory management system rely purely on human memory and hope. And in cybersecurity, hope is not a strategy.
Definitely not.
Every single time developers add a new zero-copy feature for speed, they are restarting the ticking clock on a new, inevitable vulnerability.
So if the architecture relies on hope and developers can't possibly know every unwritten rule, I mean, we have to look at what other zero-copy optimizations are quietly waiting in the dark to be exploited next.
We really do.
The briefing details some highly concerning, completely unaudited handoffs that are active right now. Let's unpack these, starting with IRing.
Okay, this is where it gets very real for modern infrastructure. IRing is the new, incredibly popular high-speed I/O engine in Linux. It essentially gives applications a direct mailroom slot to the kernel. Applications can register their own memory buffers directly for the kernel to use, bypassing traditional safety checks to achieve maximum speed.
So if a kernel path writes through one of those direct mailroom buffers, straight into the page cache without checking the sticky note, boom,
Yeah.
the exact same pattern as Dirty Frag.
Precisely. Next, look at graphics cards. Modern GPUs share page cache memory with the main CPU through a mechanism called DMA buff. That stands for direct memory access.
Direct memory access.
The key word is direct.
The GPU bypasses the CPU entirely.
It does. Hardware talking directly to hardware. The GPU could write to a page, but the CPU still thinks the page is clean and unmodified.
Oh, that's bad.
Yeah, the file system might then write the wrong version of that data to disk. Two entirely separate departments, same physical pages, absolutely no central tracking.
Wow. And the briefing also mentions NVMe drives doing direct placement. This is your physical hard drive placing data directly into the page cache memory, bypassing the kernel buffers entirely. And there are user space tricks too, right? Using commands like vamp splice and userfault FFD to manipulate exactly when the kernel thinks a memory page is ready.
It is all the exact same shape of vulnerability, just using different newer tools. I want to be clear though, none of these specific handoffs are publicly known to be vulnerable today.
Okay, that's a small relief.
But crucially, none of them have been systematically audited either. No one can definitively answer the core question, which is, does the receiving end of these high-speed handoffs actually know what kind of memory it is holding?
So for you listening to this, you might not be writing C code for the Linux kernel, but if you run Linux servers, if you manage databases, or if your business relies on cloud infrastructure, you need to act on this.
Absolutely.
The practical takeaway here is highly actionable. You need to go to your cloud provider or your internal security team and ask them one specific question. When was the last time someone systematically checked every zero-copy path in our environment for missing labels?
And when they give you a blank stare, they tell you it's impossible to audit dynamically, you know exactly where the next major zero-day vulnerability is hiding.
Yep.
The baseline assumption must be that every single zero-copy optimization has this trust problem until mathematically proven otherwise.
To summarize the thread of this briefing, we've explored 3 major bugs spanning a decade: Dirty COW, Dirty Pipe, and Dirty Frag.
All devastating.
Right, and we've seen how they all exploit one shared whiteboard, enabled by an architecture that aggressively refuses to hire a librarian to oversee it.
Yeah, that library is a mess.
The Linux kernel isn't going to suddenly become 30 million lines of formally verified, perfectly safe code overnight, which means the attack surface is still wide open.
The page cache is the beating heart of system performance. It isn't going anywhere. And honestly, the demand for zero-copy performance in AI and cloud computing is only increasing.
So the structural flaw remains untouched.
It remains untouched.
I want to leave you with a chilling thought that builds on something mentioned briefly in the text. The briefing notes that ancient shortcuts functions like send file have been in the kernel for decades.
Oh, yeah.
They are the original zero-copy paths. And because they are so old, security researchers largely ignore them, just assuming someone else already checked them 20 years ago.
Right.
Consider this. In the world of open source security, the most dangerous code isn't always the complex, shiny, new experimental feature.
No, it's not.
Often, it's the foundational legacy infrastructure that is so ubiquitous it has become completely invisible. If a catastrophic bug could live in the UDP code for 9 years just because of one forgotten sticky note, what happens when we discover that a fundamental protocol the entire internet relies on has been missing a warning label since the 1990s, simply because we all blindly assume the original architect remembered to write it down?
Thank you for listening to Zero Day Brief.